Well, as we have seen till now, the data path that we have designed has many control inputs, okay? The signals driving these inputs can be defined and organized into a control word. So we will have a control word which includes all those control inputs. And then, as we see, in order to execute the micro operation, micro instruction, we will apply control word values for a clock cycle. And for most micro operations, the positive edge of the clock cycle will be needed. The positive edge, the rising edge of the clock will be needed in order to perform the register load. The data path control word format and the fields that we have for it are shown in the next slide. So here we have a representation of the data path that we already had discussed. Looking at the register file, you can see that we need to have the right input. So this is one control word. Then D address, A address, B address are also among the other control words. The MB for the max B, function select, MD in order to select between the output of the function unit and the data in, which may come from the memory, are also the other elements that we are going to have in our control word. Yeah? In front of each one of them, you can see an index, a number indeed, 0. It indeed determines the location, the position of the control element within the control word. 6 is here. You can see 10, 11, 12. Then 13, 14, 15 here. 7, 8, 9 for B address. And 1 for MD. And now if we put all of them besides each other, over here we will have the control word with the fields determined. It has 16 bits, our control word, so it is in the form of 2 bytes. The first 3 bits are for, the most significant bits are for DA, data address, A address, B address, MB, function select, which has 1, 2, 3, 4 bits, MD, and write. So DA, I just mentioned, D address, A address, B address, max B, function select, max D, and write. And then in the next slide, we can see the connections to the data path that we just discussed already. You can see here how we have the control word encoding. So DABA, AABA, MB, FS, MD, and write. For FS we have 4 bits. For MB we have a single bit, and for DA, AA, and BA, for each one of them we have 3 bits. Okay. For MB we have a single bit, and for write we have also a single bit. So since for DA, AA, and BA we have 3 bits, they can go from 00 up to 111, 000 to up to 111, and therefore they can refer to the registers. They are addresses, yeah, with R0, R1, R2, up to R7. So that's what we have for the D address, A address, and B address. And then MB is a single bit. It could be either 0 or 1. If it's equal to 0, a register is selected, and if it's equal to 1, the constant input is selected. If you remember, MB is the multiplexer B, which is used in order to pass the constant input. For the function select, we have 4 bits. It starts from 0, 0, 0, 0, and it goes up to 1, 1, 1, 0 that you can see here. And these are the operations that we could perform within our ALU plus shifter. MD is the single bit, 0 or 1. If it's 0, then we get the result of the ALU or function unit. If it's 1, we get the data from outside, from the memory, let's say. And then write is a single bit, RW, register write. Indeed, if it's 0, we don't write into our register file, and if it's 1, we write into our register file. Over here, you can see examples of microoperations for the data path. We have the symbolic representation first. Let's say we want to perform this operation, R1 receiving the value of the result of the subtraction of R3 from R2. So you can see how the values for DA, AA, BA, MB, FS, MD, and RW are determined here. DA is the address of the destination register. So it should be referring to R1. AA is the address for the first, let's say, source register. So it refers to the first element here, R2, and BA refers to the second one, which is R3. With the MB, since here we don't have any constant value, we need to refer to the register, and then for the function select, we need to perform this operation. Okay, so A plus not B plus 1, or the 1's complement of B plus 1. And then for MD, we have to refer to the function. We don't get the data from outside. And register write will be referring to the case in which we have writing of the operation. Writing into the register, yeah. In the next slide, you can see the corresponding values. So DA was referring to R1. So the value that we need to have for it is 001. A address refers to R2, so it will be 010. B address refers to R3, it will be 011. MB is equal to 0 because we don't take any constant input. FS is 0101, which refers to subtraction operation. MD is equal to 0 because we don't read from outside input data. This means that the result of function unit is considered, and register write is equal to 1 because we are going to write into R1. And similarly for the other cases, you can also follow it. For example, in the second case, we have shifting the content of R6 towards left by 1 bit position and then writing the result into R4. Let's go through it together. So destination address refers to the data address refers to the destination register, R4. Here we don't have A address. B address refers to R6. Okay, for our shifter. We are referring to the register. We don't take any constant input. Function select needs to perform indeed this shifting towards the left of the content of the B. We don't take any data from outside, and then register write is should be equal to 1 in order to write into the register. And here you can see the corresponding actual values for the DA for the control word in it. Yeah, R4 is determined here. AA is not important, so it is don't cares. BA is 110 because we refer to R6. MB is still 0. Function select is 1110 in order to perform shifting towards the left by 1 bit position. MD is equal to 0 and WR is equal to 1. You can go through all the operations on your own, and then you will see how each micro operation is shown symbolically as we did it for the first two micro operations here, and then how the corresponding actual values should be determined for the control word. In the last slide here, you can also see the data path simulation. The first one shows you the clock. So we have one clock path, second, third, and so on and so forth. For each clock path that you see here corresponds to one of the actions that micro operations that we have here. Maybe I can give a number here: 1, 2, 3, 4, 5, 6, and 7. Okay, so in the first clock path that you see here, the first micro operation will be performed. This is what we have for the first microoperation. Then we have the second microoperation, which will be performed during the second clock pulse. So what you can do here is that, let me do it for the first one. In the first microoperation, we have dA equal to 0, 0, 1. So dA here has the value of 1. Okay, so the value is shown in it. Then for AA we have 2. AA is 0, 1, 0. AA is 2, as you can see. Then BA is 0, 1, 1 or 3. BA is 3. Function select is 0, 1, 0, 1, which is 5. So function select is 5. We are not using constant input, so it is X. MB is 0. MB is 0. It's here indeed. This is MD. MB is equal to 0. So MB is 0. And then address address out, data out, they are showing indeed what we have at the output of our register file. Yeah, register file. If you remember, over here we have the A data, which refers to the address to be written into the RAM, in our RAM, and here we have the data. So this is data input to the memory, and this is address input to our memory. So address out is also equal to 2 because it is the same as A address. And then for the data out, we have it for the data out, which is here. It is, so here A and B address, it is also the same as what we have for BA. Data in, we are not, this is data in, so we are not using it for now. It is not important. And then for MD we have it 0. MD is equal to 0. MD is equal to 0. Register write is equal to 1. So register write is equal to 1. And then in the next 8 rows, you see the content of the registers. Register 0, 1, 2, 3, 4, 5, 6, and 7. They initially have some, let's say some values. R0 is equal to 0. Register 1 is equal to 1. And down to register 7, which is equal to 7. And finally, at the end, we have the status bits, which include the overflow, carry, negative result, and the 0. So the first operation that we had was to subtract the content of R3 from R2 and store the result in R1. So R1 will receive R2 minus R3. If we look at R2 and R3, you can see the content of them here. So 2 minus 3 will give us minus 1, and if you want to write it into R1, it will be in the form of, well, let me maybe explain you. We want to perform 2 minus 3. We have 8 bits for each register. So 2 and 3 are, let's say, positive numbers. If we use 8 bits of the 8 bits for each register, 2 will be in this form, minus for 3 we will have this. And in order to perform this operation, instead of performing the subtraction, we can do addition. We just need to take the ones complement of the second number and then add add 1 to it. So we will have 0, 0, 1, 1, 1, 1, 1, 1. We will do this addition, and if we do so, let's see what we get here. Yeah, we will have 1, 1, 1, 1, 1, 1, 1, 1. So all 1 will be the result of the operation. And in decimal, this all ones means 255. And we also see that the result of the operation is negative. Yeah? Since the most significant bit here is 1, it means that we have a negative number. The actual value that we have is indeed equal to -1, 2 minus 3, which is equal to -1. This is a negative number. If you want to find out the equivalent decimal number for this, I'm sure that you could see that it is equal to -1. And on the other hand, since the result is negative, we have the status bits giving us the value of 2. For the status bit, we have V, C, and Z. The result is not 0, so this is 0. The result is negative 1. We don't have carry out 0, and we don't have overflow 0. So this is indeed decimal value of 2 that you can see over here. The resulting value 255, which needs to be written into R1 here, appears at the next rising edge of the clock. Yeah, so the content of R1 is updated at the next rising edge of the clock to 255. So this is how you can follow each operation. I'm sure that now you can focus on the second operation. We want to shift towards the left the content of R6 by 1 bit position, and then the result will be written into R4. For R6 we already had 6, so R6 was indeed filled with zeros and ones in this form. Now the content needs to be shifted towards the left by 1 bit position, so the result will be like this, which needs to be written into R4 if I'm not wrong. Yes, R4 will receive that, and you can see that in decimal this is equivalent to the value of 12. Okay, and I'm sure that you see that 12 is written here into R4 at the next rising edge of the clock. What do we need to have for D address, A address, B address, and function select? You just need to follow the required control code that we need to have, and also the addresses of the registers. DA is 4 because we are going to write into R4, and BA is also equal to 6 because we are going to perform the shifting operations on R6. Function select is equal to 14 because we want to perform the shift towards the left micro operation, and you can, I hope, you will be able to follow how the content of the registers are also updated as well. And for the status bit, in this case, you can see that it is equal to 0 because we don't have a 0 as the result. The result is not negative. We don't have carry, and we don't have overflow.